If you pour clear water over a greasy surface, the water beads up and rolls right off. It leaves the oil completely untouched. And if you try to scrub that grease off your hands using just water, the grime only smears. The mechanical friction moves the mess around, but the water refuses to grab onto it. Heavy, carbon-based grime, like the thick coal dust covering these miners, clings stubbornly to skin and fabric. Brute force alone isn't enough to lift it. This happens because water and grease are immiscible. They have contrasting molecular structures that physically prevent them from ever mixing together. Water is what chemists call a polar molecule. It acts like a tiny magnet with a positive end and a negative end. Grease, on the other hand, is nonpolar, made up of long, entirely neutral hydrocarbon chains. These greasy, nonpolar molecules are chemically almost identical to the long-chain hydrocarbons pulled from the Earth to make fossil fuels and motor oil. Because water molecules are tiny magnets, they strongly attract each other. Clumping together, they squeeze out the neutral hydrocarbon chains. On a macro level, this rejection creates two impenetrable layers, locking the oil and water apart. To bridge that boundary, you need a molecule that speaks both chemical languages, a mediator that can grab a neutral oil chain with one hand and hold on to a charged water molecule with the other. That mediator is the soap molecule. It is engineered with two ends that have entirely opposite chemical desires. One half is the hydrophobic tail, a water-fearing chain of carbon atoms that dissolves into fats. The other is the hydrophilic head, a charged carboxylate group that acts like a magnet, drawing itself towards water. When placed between the two fluids, the molecule physically stretches. The tail burrows into the grease, while the head anchors firmly in the water. This dual nature makes soap a surfactant, or surface active agent. It interrupts the tension at the boundary line, allowing two normally hostile liquids to interact. The moment you introduce soap into greasy water, the hydrophobic tails desperately seek cover. To escape the polar water molecules, they plunge straight into any droplets of grease they can find. The tails submerge completely into the oil, while the water-loving heads stay perfectly aligned on the outside. Thousands of soap molecules swarm a single droplet of oil, forming a tightly packed three-dimensional sphere called a micelle. As the micelle forms, the physical force of the soap molecules wedging themselves in lifts the stubborn grease right off your skin or clothes, suspending the entire droplet in the water column. It's essentially a chemical disguise. By trapping the oil inside a shell of water-loving heads, the soap makes the grease look like a soluble sphere. Because the micelle's exterior has charged heads, water molecules accept the package, flowing smoothly around it. Multiplied by millions, the solution suspends countless grease droplets. The hydrophilic heads repel each other, keeping droplets bouncing apart and preventing grime from resettling. The soap hasn't actually dissolved or destroyed the oil. It has simply packaged the grime into a custom-built container that water is finally willing to transport. This brings us to the rinse. When you turn on the tap, the flowing water catches those suspended micelles and sweeps them down the drain. The heavy, non-polar carbon grime that water couldn't budge just moments ago is stripped away completely, leaving the skin perfectly clean. We defeat that stubborn dirt not through sheer force, but through the dual nature of a simple carbon chain. That molecular quirk takes two completely incompatible liquids and forces them to finally cooperate.